Good morning, everyone. My name is Taoan. Today I'm presenting on leveraging AI for water infrastructure resilience. This is a joint work with my advisor, Bisrat Yakina, and several master student, Kishan, Serena, and Paritosh. So water infrastructure is very important to our life because it provides access to drinking water, and it also functions like fire departments, hospitals, schools, and many other important facilities. But they are extremely vulnerable to natural disasters like earthquakes. So designing strategies to improve resilience against earthquakes is a very relevant task in many cities in the US and around the world. So Los Angeles, for example, has a very high seismic hazard exposure. So the city has an ambitious goal of forming a system-wide seismic resilient pipe networks. So they want to replace some of the old pipes with earthquake-resistant pipes so that during an earthquake, these pipes are less likely to be damaged, and so they can guarantee continuous water delivery to certain locations and also help restore water supply in areas suffering from water shortage. So building such networks has to meet several requirements. First, it has to be cost optimal, and also critical customers like hospitals, fire stations, police stations, etc. They must be directly connected to the resident network. And also all the housings and buildings, including all the residents, must be within a certain proximity of the network, so they have they are close enough to water during or when there are water shortage. So there are many challenges because there are exponentially many choices and very complex constraints to deal with. And the other challenges come from sequential comes from installing the network. So even though if we can obtain the optimal plan, it is very difficult to install the network in a short period of time because of limited budget and resources and difficulty of construction. So in 2019, Los Angeles has already installed 2.6 miles of pipe, and they plan to continue to upgrade about 40 more miles of pipes in a 3-year period. So in this situation, it becomes very important task to effectively determine which part of the pipe should be selected for each period of installment to maximize efficiency over time. So we have we formulate this problems as combinatorial optimization problems and provide scalable and efficient algorithms to solve them. Without going into too much details about the algorithm, let's look at some results produced by our algorithms on 2 8-mile by 8-mile region in the city of Los Angeles. So here we can see in the figures, the pipes are colored in different the pipes are showing different colors. Green pipes are those in the safe zone, whereas the blue and red pipes are those in the hazard zones. So for example, blue pipes are in the liquefaction areas and red pipes are in the fault zones. And customers are represented as the dots. Black dots are those in the safe zones and purple dots are those in the hazard zones. So they are more likely to be threatened during an earthquake. So our goal here is to optimize the placement of resilient pipes. So they are showing the light blue segments here. So they can guarantee to safely bring water from the safe zone to customers in the hazard zone they are threatened during an earthquake. So our tool can also recommend which sets of pipes to install in different period of time. So and so we can also provide visualizations to see how the pipe networks grows to reach customers over time. They are showing the yellow color segments. And also our algorithm can also provide cost-benefit analysis by to study the trade-off between different budget allocations and the speed of gaining benefits from the network. And finally, on the practical side, we have developed a software tool, and this has been transferred to our partner at our Department of Water and Power. We give them our code and documentation, and we have done training with their engineers. They are now able to run the tool with their own data. And the next steps include interviewing more stakeholders to understand their needs to make the tool more robust and easier to install, use, and maintain in the future. Thank you.